Okay, this is exam 3 for fall 2009 for Physics 101. First one, we have a 100 kilogram merry-go-round of radius 1 meter. It started from rest by a constant horizontal force of 50 newtons. Find the angular speed after 3 seconds. So the angular speed is omega. That's equal to omega naught plus alpha t. It says that it starts at rest, so omega naught equals 0. So that goes to 0. T is equal to 3 seconds. So I need to find out what is alpha. Alright, I know that the torque is equal to F times R, and that's also equal from Newton's second law to I times alpha. So I can say then that alpha is equal to FR over I. F is equal to 50 newtons. R is the radius, that's 1 meter, and then I is the moment of inertia. For a disk, this is 1/2 mr squared. So that's 50 times 1 times 1/2 of 100 kilograms times 1 meter squared. So that's 50 over 50. So the moment of, the angular acceleration is 1 radian per second squared. And so bring that over here. Omega then is equal to 1 radian per second squared times 3 seconds. So it's 3 radians per second. So the answer is A. What happens when a spinning figure ice skater moves her arms out away from her body? When she moves her arms, she increases her moment of inertia, and so the angular velocity goes down. So which of those, let's see, her moment of inertia increases, her angular velocity increases, that's not true, that's not true, neither of these are true, so it's A. A thin hoop with a mass of 0.5 kilograms and radius 1 meter is spinning at 10 radians per second. What is the energy of the hoop? Kinetic energy is 1/2 I omega squared. The moment of inertia for a hoop is just mr squared times omega squared. So this is 1/2 times m, which is 0.5 kilograms, radius squared, which is 1 squared, omega, which is 10 squared. It's a half, quarter of 100 is 25, which is D. These 1 kilogram masses are connected by light inflexible rods. They're rotating about the axis as shown. What is the moment of inertia for the system? Well, moment of inertia is equal to the sum of mr squared. So we sum up mr squared for each individual particle. But here r is equal to 0, and here r is equal to 0. R is the distance to the axis of rotation, and those two particles are on the axis of rotation. Alright, so we also want to know this distance. I'm going to draw a triangle here. I'm going to redraw it over here. This is the distance r. This is 0.5 meters, and this is 1 meter. So to solve for r is equal to 1 squared minus 0.5 squared, the square root of that, and that is the square root of 0.75. I'm just going to leave it like that. Now, if I want to know the moment of inertia, it's just mr squared. M is 1 kilogram. R is the square root of 0.75. And then that squared, and the square root of 0.75 squared is just 0.75 kilogram meter squared. And that's C. Buckets are spinning horizontally on frictionless bearings. Suddenly it starts raining. Which of these statements is true? Well, the rain falls into the buckets. That increases their mass, which increases their moment of inertia. So the moment of inertia increases, so their angular speed or their angular velocity will decrease. And that's what it says in option A. That, by the way, is very similar to a problem that we had before where the cart was traveling and the rain fell into it. This is a Pascal's principle. Pn is equal to P out. That is Fn over An equals F out over A out. Says that you put on a force of 12 newtons on the brake pedal, so 12 newtons over the area right here, over this area, is 2.1 centimeters squared, and that's equal to F out over the area of your slave cylinder or your brake cylinder, which is 6.3 centimeters. And then if we solve this for F out, it gives us F out is equal to 36 newtons. You have to cross multiply here and divide by 2.1. That's A. The artery becomes clogged. Which of these statements describe the flow of blood through the clogged artery? Well, the velocity increases by the equation of continuity because the area decreases, and by Bernoulli's principle, the pressure is going to decrease in the clogged artery itself. And so velocity increases, pressure decreases. That is C. Options for number 7. This figure shows a barometer, which the pressure at the top of the tube is 0. It's filled with water. The pressure outside is 2 atmospheres. We know that P is equal to P0 plus rho g h. That is 2 times 10 to the 5th. That's 2 atmospheres. Is equal to 0 plus 1,000. That's the density of water times 9.8 times h. And we solve this for h. We find it's equal to 20 meters. 2 beakers are filled to the brim with water. Both beakers are weighed. You put a steel block in one, which sinks. Which scale reads the larger weight? The second scale reads the larger weight. The steel displaces a certain amount of water, but the weight of that displaced water is less than the weight of the steel. That's why it sinks, because the buoyant force is less than the weight of the object. So beaker 2, that's B. Boat has a volume of 1 cubic meter. If the boat has a mass of 500 kilograms, what fraction of the boat is submerged to the water? Well, if it was fully submerged, your buoyant force would be rho Vg. That's 1,000 times 1 cubic meter, which is your volume, times 9.8 meters per second squared. So that's 9,800 newtons. That's your buoyant force if it's fully submerged. Now the actual weight of it is mg, which is 500 times 9.8, which is 4,900 newtons. So the weight is 1/2 of that buoyant force. So that means that the boat is going to be just halfway submerged. Metal has a density of 1,200 kilograms per cubic meter. What is the mass of the block that has a volume of 4 cubic meters? Well, rho is equal to m over v. We want to know m. That's rho times v. 1,200 times 4 is 4,800. That's A. Mercury barometer at atmospheric pressure. The height of the column in mercury is 760 millimeters. If another mercury barometer is used that has a tube of larger diameter, how will the column of mercury be in this case? Well, P is equal to rho GH in this case for a barometer. You see, it's not dependent upon the diameter, so it's going to have the same height. Okay, you have this fluid flowing through this pipe. You have these 2 standpipes that are an indicator of pressure. We had added that sentence in this problem. The level of the fluid in the pipes A and B is an indicator of pressure. Now, the pressure here, P1, is larger than P2. Alright? And since P1 is larger than P2, you're going to have a higher level of fluid in this pipe than you do in this pipe. So in which standpipe is the level of fluid the highest? It's going to be A. Number 13. Number 14, a cylindrical glass sleeve is to be shrink fitted over a brass shaft whose diameter is 2.172 centimeters at 0 degrees Celsius. The diameter of the sleeve is 2.154 at 0 degrees Celsius. What temperature must the sleeve be heated? So we're talking about the sleeve. The initial diameter of the sleeve is 2.154 centimeters. The final, we want it to be the same as the shaft, so it's 2.172. The initial temperature is 0 degrees Celsius, and the coefficient of linear expansion is given here. Now we know that delta L is equal to L naught alpha delta T. We want to know what delta T is, so that's delta L over L naught times alpha. That's 2.172 minus 2.154 divided by 2.154 times 19 times 10 to the minus 6. And that's equal to 440. It actually didn't ask for the change in temperature, it asked for the final temperature. But since our initial temperature, T final, since my initial temperature is 0, then T final is equal to the change in temperature. So T final equals 440. ideal gas occupies a volume of 1 cubic meter at 10 degrees Celsius and atmospheric pressure. Determine the number of molecules in the gas container. Use the ideal gas law, PV equals nRT. The pressure is 1 atmosphere, so that's 1 times 10 to the 5th pascals. The volume is 1 cubic meter. We're solving for N, which is the number of moles. 8.314 is the ideal gas constant. That's in joules per mole Kelvin. And because that's in Kelvin, we need to convert our temperature, 10 degrees Celsius, to 283 Kelvin. Just adding 273 to it. And if we solve for N, which is the number of moles, is 43 moles. But I want to convert that into molecules, so I multiply it times Avogadro's number, 6.02 times 10 to the 23, which gives me the answer, which is 2.6 times 10 to the 25 molecules. The SI unit for temperature, the Kelvin, is based on what part of these, on which of these physical quantities? Okay, well, it's not the freezing point of water. It's not the pressure of water at which sublimation occurs, and these are just sort of, these don't really have any meaning. It's B, the temperature of the triple point of water. It's also based on the absolute zero temperature. Which of these best approximates the temperature of air in this room? Well, 70 degrees Fahrenheit is approximately equal to 20 degrees Celsius. You should just have a good idea for that. That's D. You want to take apart a couple copper parts held together by brass screws, but the screws are stuck. What should you do? Alright, so you have copper parts, and they're held together by brass screws. So if you heat it up, the brass, which is the screws, since it has a bigger coefficient of linear expansion, if you heat them up, then the brass is going to expand faster than the copper. So that just makes them stick more. If you heat just the screw, that's just going to make the screw bigger and it's going to stick more. But if you cool them off, since the brass has a higher coefficient of linear expansion, it's going to get smaller faster than the copper does. So you want to cool them both. So that's B. Which of these is the smallest unit of temperature? A degree Kelvin, Celsius, or Fahrenheit? The answer is Fahrenheit. A. You heat a bimetallic strip that is made of brass on one side and steel on the other. As you heat it, the strip will bend towards which side? So you have this bimetallic strip, brass on one, we'll call this the brass side and this the steel side. The coefficient for brass is bigger, and so it's going to bend towards that side, because the brass side is going to get bigger faster than the steel. So it's going to bend towards the steel side, which has the lower coefficient of friction, the steel does. So the answer is A. Heat flow occurs between two bodies in thermal contact when they differ in temperature. Waterfall is 145 meters high. What is the increase in temperature at the bottom of the falls if all the initial potential energy goes into heating the water? So your potential energy goes into heating the water. Your masses cancel here. We want to know what delta T is. That's GH over C, which gives me an answer of 0.34 degrees Celsius. That is A. Alright, 120 gram block of copper is taken from a kiln, placed into a beaker of negligible heat capacity containing 300 grams of water. The water temperature rises from 15 to 35 and give you the specific heats. What is the initial temperature of the water, the copper, when it was in the kiln? So calorimetry problem, sum of the Q's is equal to 0. So the sum of the heats is the mass of the copper, specific heat of the copper, change in temperature of the copper, plus mass of the water, specific heat of the water, change in temperature of the water. And then we just need to put in the numbers here, which is the hard part actually. So 120 grams, that's the mass of the copper. 0.1 is the specific heat in calories per gram degree Celsius. Notice that specific heats are given in grams, so I don't need to change the masses. And then the change in temperature, the final temperature of the copper is 35 degrees Celsius, minus the initial temperature of the copper, which is what I want to know, plus the mass of the water, which is 300, times 1, which is the specific heat, times 35 minus 15. That's the final and initial temperature. This is all equal to 0. This gives me 420 minus 12 Ti. Comes from this first term, just distributing that 120 times 0.1 across this. plus 300 times 1 times 20 is 6,000. That's equal to 0. And if I solve this for Ti is equal to 535 degrees Celsius. You got to be careful with your signs on this and making sure that you get the right final temperature here. Water has a higher specific heat than sand, therefore on the beach during midday the breezes blow what? Well, it has a higher specific heat than sand, so that means that during midday the sand is hot because it heats up really quickly while the water remains cool, alright, during midday. And the hot air above the sand rises and air comes in from the beach. So, from the ocean rather. So the wind is going to blow from the ocean to the beach. How much energy is required to change a 0.1 kilogram block of ice into water at 50 degrees Celsius? So the heat of water is given. I also give you the latent heat of fusions and vaporization. This should also say that this block of ice is at 0 degrees Celsius initially. So my Q is mass times the latent heat of fusion. That's the energy required to change it into water, to change the block of ice into water, plus MC delta T. That's the energy required to raise the temperature. Just put my numbers in. 0.1 kilograms is 3.33 times 10 to the 5 joules per kilogram, plus 0.1, 4186, times my change in temperature, which is 50 minus 0. If I just plug that in, I get 54,000 joules. That's A. This is B.